Hello and welcome back. And today we're going to be talking about how to show the conservation of angular momentum for straight line motion using a geometry approach. So previously we used a vector approach, and that works for some people, and for other people it doesn't. So we're going to show how to solve this problem in a different way. So we're going to start off with our little rocket ship over here. And again, I am not a graphic artist, so it's going to be a little questionable in the quality, but hopefully it will help. And our little rocket ship is moving with a velocity v, going that way. So in a time period t, it's going to move a particular distance. And hopefully I can draw these bars correctly. So we've got vt, 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 and then way out here, vt. And despite how I may have drawn them, they all should be the same length. Now, let's pick an origin point. And this is going to be the origin for our angular momentum measurement. But in this case, we're interested in the area that's being swept out over this period. So we're going to start and make some little dash marks here, little dash marks here, dash marks here. Little dash marks here, little dash marks here, and way out here some little dash marks. So all these should be the same length. All segments same length. Because of constant velocity. Okay. Now what we're going to do is we're going to go and select a pen here, and let's look at some triangles. And this is the area swept out by the ship between the starting point and this ending point with respect to our origin. So triangle area. So triangle area matters. So the area of a triangle is 1/2 the base times the height. So if we look at this line, we do a little dashed line here. Let's call this the height. And we'll call each of these the base. Let's go to a slightly different color. So for each of these triangles, even though they're shaped differently, they all have the same base, and they all have the same height. So even though they're different, let's just try shading this up a little bit more. So even though they're different triangles, they're all got the same area. Just turn this around a little bit and see if I can draw. Oh, that's the advantage of doing it like this, is that if I screw up in the middle, I can hopefully correct it. This is going to get a little bit dicier when we go out to these guys. So these triangles out here, when it's far away, are really skinny little guys, but they're also quite long. Let's see if we can do this correctly. Oh yeah, a little bit of curve on that. Artistic license. Let's see if we can get rid of that top guy. Yeah, he's just a little bit thick. So out here, this is a really, really long, thin triangle. I'm going to make my origin point a little bit clearer. So let's scroll down just a touch. So all triangles have the same height, which is just this minimum approach distance, and they all have the same base. And since they have the same height and the same base, they have the same area. So this is how we get that for an object in constant velocity with respect to a fixed point, it's got a constant angular momentum by virtue of this relationship with how triangles work. So it's sweeping out the same area. Here it's, got a triangle that looks, fairly normal in the sense it's got a nice stocky base relative to the peak. And here you've got a very, very, very slanted triangle where the base is the same distance, but it's got to go way out over here. So if we look from this perspective, it doesn't look like the rocket's moving very much. It's not changing its angle very much, but it's got a very long lever arm. Long lever arm, small angle change. So hopefully you found that instructive.